Good afternoon, all of you. We were studying about liquid state in the last class. We completed one of the properties of liquid state, which was vapor pressure. And today we will be discussing the other two properties, which are surface tension and viscosity. First, we will move on to surface tension. You all might have visited beach. And in a beach, you can see dry sand and wet sand. And when you walk through it, the dry sand will be flying due to the heavy wind from ocean. So the dry sand will be flying easily. But in case of the wet sand, it will be sticky. It won't fly in air, right? So there is some interaction between the wet sand particles. And if you try to take that to some buckets, the dry sand is very free to move. If you try to push in your hand inside, it can easily go down. But in case of wet sand, it is not possible, right? So there is some interaction between these particles or wet sand particles. We will see that. Before that, we will see one more example. Here you can see a dry paper. It is not sticky at all. But in case of wet paper, it is very sticky. If we try to stamp this paper onto a wall, it will be sticking there, right? So easily we can stick this paper to a wall just by applying some water to it. And once the water is dried off, that will fall down. So all this is because of a property known as surface tension. This also you might have observed. It is the capillary rise and you have studied it in the earlier classes. In this case also you can see the involvement of surface tension. So now we will see what exactly is surface tension. So we are taking a vessel and in the vessel we have liquid particles. For example, we can consider water. So I have taken water in a vessel. So surface tension tells us about the interaction between these particles. So all the particles in a liquid does have an interaction with each other. There is a difference in interaction when it is in the bulk and when it is in the surface. So we will see that by considering two particles, one in the bulk and one in the surface. So the one in the bulk will observe forces from all the sides. So this particle will be attracting this particle, this will be attracting this and all of them around this particle will have some interaction with the center particle or the particle in the bulk. But in the case of this particle, if you see, it is having interaction with these particles only. There are no particles above this molecule. So from above, there is no pull for this particle, right? So if you consider that in a whole, so this particle in the bulk will have interactions in all directions. So all around this particle, it is having other molecules and those particles will be attracting this towards them. So a molecule or a particle in the bulk will experience force all around it. But in case of a particle which is in the surface will experience force only in these directions. Why? Because there is no particle in this portion to attract this. So there is no interaction in these directions. But in case of bulk, there are particles all around this particle and all of them will be interacting with this. So hence this will have interactions all around, this will have interactions in these directions only. But if you consider the net force acting on this, that will be zero. Why? Because this force is cancelling this force, this is cancelling this is cancelling this. So totally, if there are forces in all the directions, one of them will be cancelling the other one. So when there are forces all around, each one will cancel off and the net force or the net interaction will be zero. But in case of the particle in the surface, it is not happening, right? There is no other force to cancel off this one in the opposite direction. So when there are opposite forces, they cancel off, but in this case, they are not cancelling off. So the net force experienced by this particle in the surface will be in this direction, right? So a molecule in the bulk of liquid experience equal intermolecular forces from all the sides, and it is not experiencing any net force as they cancel each other. But for a molecules on the surface, so net attractive force is towards the interior of the liquid. So interior of liquid means this portion, right? So the net force will be in this direction. So the force which is experienced by the particles on the surface towards the inner side of the liquid is known as surface tension. And we will see the definition now. So if we try to define surface tension, it is the force acting per unit length perpendicular to the line drawn on the surface of liquid. So we will see that, and this is the particle which is there in the surface, and the net force will be perpendicular to the surface, right? So the force will be acting in this direction, so the net force will be perpendicular to the line drawn on the surface of the liquid. So as it is having in all the direction downwards, so the net force will be downwards only. So that will be perpendicular to the line drawn on the surface. And it is the force acting per unit length perpendicular to the line drawn on the surface of the liquid. So that's the definition of surface tension. It is denoted by the Greek letter gamma. It has dimension of kilogram second raised to minus 2 unit expressed in Newton meter raised to minus 1. Now we will see what are the consequences of surface tension. You might have seen a raindrop shaped like this. So everywhere a raindrop is shaped like this. But actually how the water drop looks like? Yes, of course a raindrop will look like this, but that is because of the gravity. So when the raindrop is falling from the clouds towards earth, gravity is pulling one side of the drop towards it. So that is why, because of that pull from the gravity, this raindrop will shape like this. And if we don't consider the gravity, actual raindrop or actual drop of a liquid will look like this or in spherical shape. Even if we consider the shape of mercury drop, it will also be spherical. So usually liquids occupy spherical shape for their drops. And why is that so? We will see that. So liquids tend to minimize their surface area, and the molecules on the surface experience a net downward force as we saw just now and have more energy than the molecules in the bulk. So as they are having a net downward force towards the liquid or towards the inside part of the liquid, they will have more energy than the molecules in the bulk. So the molecules in the surface are experiencing an extra net downward force, and because of that they are having more energy than the molecules in the bulk. And liquids tend to have minimum number of molecules at their surface. So as they have more energy, liquids tend to have minimum number of molecules at their surface. And if the surface of a liquid is increased by pulling a molecule from the bulk, attractive forces will have to be overcome, and this will require expenditure of energy. So this is another point. So liquids tend to minimize their surface area, and when the surface of the liquid, which is actually minimum, and when we are trying to increase it by pulling the molecule from the bulk, the attractive forces which they have will have to be overcome. So consider these two figures. So here it is having lesser amount of surface area. That is how liquids want it. And if we try to break the intermolecular forces between these particles and we are trying to increase the surface area, this process needs some amount of energy. And that energy is known as surface energy. So the energy required to increase the surface area of the liquid by 1 unit is known as surface energy, and its dimensions are joules meter raised to minus 2. So how much ever joules we need to increase the surface area is by 1 unit is known as the surface energy. So the lowest energy state of liquid is when the surface area is minimum. We told there is more energy needed to increase the surface area. So when surface area is more, energy will also be more. Everything in nature tries to decrease its energy. The lowest energy state of a liquid is when the surface area is minimum. And when the surface area is minimum, that will acquire a spherical shape. So spherical is the shape which satisfies minimum surface area. So this is the reason why liquids acquire spherical shape and satisfies lower energy state. That's all about surface tension. Now we will move on to the next property of liquid, which is viscosity. So what is viscosity? You all have seen water flow. And what is actually happening inside this? Or if we consider few layers of water which are flowing, what is actually happening in that? We will see that now. Consider the liquid is flowing in a stationary object. So I have kept a rod or a stationary object and allowing the layers of liquid to flow in it. So there what happens is, when they start flowing, the layer which is just above the stationary object won't move at all, because this layer or the layer just above the stationary object which is touching the stationary object will have interaction between this. So there is interaction between the stationary object and the liquid layer. So this stationary object is acting some force on the layer which is touching that. But in case of the top layer, it is not having interaction with the stationary object, so it will move faster. Not only that, but this layer or the first layer which is touching the stationary object is actually acting a force on the second layer. And the second layer is also acting a force on the third layer. So what is actually the force between them? That is nothing but the friction. So when we try to push something over another material, there is some amount of friction acting between these levels or these layers. So it is the same case, or the same friction is acting in these layers. So there is friction between the stationary layer and between the first layer of the liquid. And there is friction between the first layer and the second layer, and between the second layer and the third layer, and goes on. So that friction is actually against the flow. So there is a particular amount of resistance against the flow because of the friction by these layers. So all these layers are having frictional force between each other, and that frictional force is resisting the flow of the liquid. And this force is known as viscosity. So viscosity is the measure of resistance to flow which arises due to the internal friction between layers of fluid as they slip over. When a liquid flows over a fixed surface, the layer of molecules in immediate contact of the surface is stationary. This we have discussed. So the ones or the layers which are actually in immediate contact with the stationary object will be stationary. So as this is a fixed surface, there will be high friction between or a high interaction between these stationary object and the layer which is touching that. So there is an interaction between these two, and so this layer is stationary or not moving at all. The velocity of upper layers increases as the distance of layers from fixed layer increases. So there is a velocity gradient between these layers. If we consider this as the stationary layer, the layer which is touching the stationary layer will move a little slower. So that is also a known fact. One is actually stationary and this layer will move slower than this layer. This layer is far from the stationary layer, so the first layer will move faster than this layer. So as it is having lesser interaction between this layer, this will move faster. So the velocity of upper layers, if there are more layers in the top, then they will have more speed than any of this. So as the distance from the stationary layer increases, their velocity also increases. The type of flow in which there is a regular gradation in velocity in passing from the layer to the next is called a laminar flow. So that is an important point there. So here is a gradation of velocity, of decrease in velocity as it comes close to the stationary object. So this type of flow where there is regular gradation in velocity in passing from layer to layer. So this layer is faster than this is faster than this one as it goes. So this type of flow is known as laminar flow. And if we consider these as plates or the layers of liquid as plates, distance between these two plates, let it be dz, and the velocity difference will be du. So if this velocity is u and the next velocity will be u plus du and the next one will be u plus 2 du, next will be u plus 3 du, like that it goes. So the velocity difference is du and the distance between the plates are dz. So we will see what the viscosity actually depends on, or what viscosity is proportional to. So first thing is the velocity by distance between them. So how much is the velocity by distance between the plates? So the viscosity or the viscosity force is proportional to du by dz. Du is the velocity difference and dz is the distance between them. So F is proportional to du by dz. So next is the area of the plate or area of the layer. How much is the area which is flowing? That is also dependent to the viscosity. So F is proportional to A also. So we have F proportional to du by dz and F proportional to A. Together we can write F is proportional to A into du by dz. And if we take this equation and remove the proportionality sign, it will become F is equal to a constant which is known as eta. To remove the proportionality sign, and it becomes F is equal to eta into A du by dz. And this is the equation for viscosity, where eta is the proportionality constant and is also called as coefficient of viscosity. And if we try to find the value of eta, how it can be? So the coefficient of viscosity, we need to take it to this side. It becomes 1 by eta. So 1 by eta is equal to F. If we take this side, it becomes 1 by eta is equal to A du by F dz, right? So 1 by eta is equal to A du by F dz. And if we take 1 by eta as eta, then we have to take the reciprocal of it. Hence, it will become eta is equal to F dz by A du. So this is the equation for eta. And how we can define eta? Viscosity coefficient eta is the force when velocity gradient is unity and the area of constant is unit area. So if the velocity constant dz by du becomes 1 and even the area becomes unity. So finally all these terms, if A and dz by du becomes 1, then the eta will be equal to F. So eta is equal to F or the viscosity only. Thus eta is the measure of viscosity. And the SI unit of eta, the viscosity coefficient, is Newton second meter raised to minus 2. That's all about viscosity and surface tension, and with this we finish our chapter. So there are a lot of examples for surface tension and viscosity is given in your textbook. So please go through that while preparing notes. And now prepare notes and submit. Thank you.